I recently made a video about all the components of a DC-DC synchronous buck converter. I wanted to see how this looks like under a thermal camera when it is loaded. I did not want to break the board, so I added a load which was drawing about a few hundred milliamperes of current. Now, as soon as the board is powered up, we can see that the MOSFET starts heating up right away. This is because of two main loss mechanisms. One, the switching loss. Every turn on and turn off event, the switch briefly has voltage and current at the same time. That overlap repeated every switching cycle adds up and starts heating up the MOSFET. The second loss is called the conduction loss mechanism. That is, the current through the switches on the resistance heats it up like any other resistor, that is the I square R loss. So a higher load current would heat up the MOSFET more. We can see that along with the MOSFET, the inductor also is heating up. The inductor also has two main loss mechanisms. First is the copper loss. That is basically the windings resistance heating up from the current running through it. The second is the core loss. The core is magnetized and demagnetized every cycle, and that constant flux reversal costs energy as heat. Now, why does nothing else heat up? The capacitors are just storing energy and releasing the charge. They're very low loss components. And the other part is all of these smaller resistances on the system. Those are also very high values, so they don't have a lot of loss associated with that. And this is exactly why thermal imaging matters during the design. It is a direct feedback on where the losses actually are, not just the components, but where physically on the board. And it can catch things that you did not model initially: uneven current sharing, hotspot from a poor copper pore, a component running hotter than expected. Thanks for watching, and please leave a comment on what circuits you would like to see under a thermal camera.